Yo, shout out, much love to the shooters, everybody looking to improve your shooting ability by improving your understanding of the physical laws of the universe, what it means to push a ball up into the air and have it fall through a hoop. This will definitely help you. This is Physics and Mechanics of Shooting Part 1 of about a dozen, so we're dropping these slowly, really taking our time on this to make sure that everything is legit. It's not going to be perfect, but it's really important that the physics in here is easy to understand and makes sense. So if you want a link to this document, drop your email below. If you're already on the subscriber list, you'll get an email today. For each segment that drops, we're going to go through and do a video on it to explain it, to make it easier to understand. So this is the outline. Today we're just looking at the physical terms and definitions to get started. It's really important that we understand the basics of physics, which is what this video is about. So just to start off, physics is the study of the physical laws of the universe. Mechanics or classical physics is the study of the interactions between objects resulting in motion. So this is just the key to all of this. And you will notice that a lot of the stuff in this is color coded. And that is intentional in order to develop color associations for faster learning. This will confuse some of you, but I think it will help the majority of you as it helped me. So we're coloring throughout this book. Interactions, force interactions are in red. This can be a push, a pull, anytime two objects are working on each other, or pushing on each other, pulling on each other, causing movement. Any kind of object we have in dark red. So me, you, the ball, the hoop, the earth, the ground have mass. Mass is dark red. Resulting in motion. We're looking at free motion here, not motion interactions between objects, just when something is moving. So we're going to use orange to describe that, orange arrows and such. So I feel that this is simple and an easier way to understand than if we're just in a black and white world. So red interactions between dark red objects resulting in orange motion. And there's going to be more colors that will sprinkle in here. So when we understand this, we can understand the physics of shooting red, a basketball, us shooting a basketball, dark red, towards and aimed. We're looking at directions in the blue spectrum. So we have purple, pink, and blue to look at up, down, left, right directionally. So let's go into the important physical and mechanical terms, and that's what this video is about. In the next couple videos, we're going to start getting into the specifically how shooting a basketball works more. So speed, probably generally aware of what speed is just how fast an object is moving. Distance over time, the greater distance something travels, the greater the speed, the less time something travels the same distance, the greater the speed. However, something important to note is that it's not directional. In physics, this is called a scalar. What this means is we can throw a ball at 30 miles an hour, but that doesn't say where it's going. So on the other hand, we have velocity. Velocity is like speed, but it's directional. So a ball that's shot at 30 miles an hour might have a directional upward velocity and a forward velocity that add up to 30 mathematically. It's not just straight addition. We use a Pythagorean theorem in order to do this, right? So total speed is not directional, but speed is made up of velocities, right? So we have forward velocity and we have upward velocity. So we're using orange to look at speed, velocity, anything that's movement. Purple, pink, blue, the directional spectrum. Pink is up, forward is purple. I know these are a lot of colors to memorize or whatever. You don't need to memorize them. It'll make more sense over time. So velocity is like speed. Well, velocity equals speed. That's not true. Velocity is changed in position over time. Not how fast something's going, but how it's changed in position. So it describes direction. So if you want to calculate speed from velocity, it's just the Pythagorean theorem. You probably remember this from math class, and if not, you're gonna kill math. This going through this book will make, if you're in high school, this will make, or middle school, this will make your classroom shit so fucking easy. Excuse my language, but it's fun to swear sometimes. Anyways, so we have total speed squared equals upward speed squared plus, or sorry, upward velocity squared plus forward velocity squared. So for instance, Say that we shoot this ball and we release it right here. At the time we release it, say at a speed of 21 miles per hour. That speed could be comprised of 15 miles per hour vertical, 15 miles per hour horizontal directional velocities. It's important to break speed down into velocities because we're going to be looking specifically at what causes upward velocity arc, what causes forward velocity range. So it's important to break these up. Okay, so vertical velocity is going to be affected by gravity pull. Gravity is a force in red interaction, and it causes downward pink. But for upward, we're using regular pink. For downward, we're using outlined pink. But anything pink is the up-down direction. So the gravity is going to pull this ball down, but it's basically going to stay on the same speed forward, only with friction from the air and friction from the ground or the hoop or whatever. But basically, the up-down velocity is going to change throughout the flight path, but the forward one's going to stay the same. Acceleration. I know we have a lot of the same things in orange, but there's only so many colors the human brain can comprehend, and we're just using orange for everything that is strictly used to describe motion. So acceleration is the rate of change of velocity of an object. It's how fast something is moving faster. Sorry, it's if something is moving faster or moving slower, we can describe that as acceleration. Now, like velocity, acceleration is directional, which is a vector is the word for that, but directional works just fine to describe that. So acceleration is the result of red forces acting upon a dark red object. Force causes an object to accelerate depending on its mass. We're going to get into this when we get into Newton's laws in a moment. So acceleration is change in speed, acceleration is change in velocity, acceleration equals force over mass. So basically, if I push or pull on you, depending on how much I weigh or have mass compared to you, it will result in you or I having acceleration resulting from that push, right? Okay, right, so for example, if we cause the ball to move from start to release, we're accelerating the ball upward vertically and forward horizontally, increasing the ball's upward velocity and forward velocity. It's moving faster and faster up to the point of release, right? And after release, gravitational force acts as downward acceleration, right? So acceleration is directional. When something's slowing down, it's actually accelerating downward, right? Now we'll get into force. We talked about force as an interaction between objects. It could be a push or a pull. It's directional, so you can push upward, you can push forward, you can push backward, etc. Force causes acceleration depending on mass, which changes velocity. Force equals mass acceleration is really something important to remember for shooting and in general for anything. So anytime we're applying force, depending on the mass, depending on the acceleration, or depending on the force, depending on the mass, may affect how much the acceleration is, right? Something important to consider is static friction. So static friction is what causes something to stay in place even when force is applied. Imagine if you try to drag a sled. Even if you pull on that sled, it may not move because of static friction. But once it starts to move, static friction has been overcome, then force causes mass times acceleration. So this is a small but key point to keep in mind. Now we look at mass. Mass we can think of being similar to weight, but it's weight times gravity pull, right? So for instance, mass is the amount of matter in an object. Our weight is going to be different on Earth than it's going to be on Mars or in outer space, but our mass is going to be the same because we're looking at how it affects gravity pull. Mass is important to consider because in force interactions between objects, depending on the relative mass, results in different kinds of acceleration. If I'm really, really heavy and I apply force, the ball is going to go flying, right? Or if the ground is really, really heavy, I apply force on the ground. I shouldn't say heavy, has high mass. It's going to throw us up. It's going to push us, right? Makes sense? All right, moving on. There's a few more. We're about halfway done with this segment. There's a few more physical terms and definitions we need to get to. Potential energy. Potential energy is stored or pent up energy in objects from surrounding forces. So For instance, if you're squeezing a ball, you're applying pressure. The ball is not moving, but it's been filled with potential energy. And if you remove one of your hands from the ball, that's going to turn into kinetic energy and it's going to go flying. Alternatively, we can think of potential energy like we throw a ball up in the air. Even though it's going up, the gravity, which is pointing downwards, gravity pull is giving it potential energy, which as it turns around in midair is going to have kinetic energy. Although potential energy is not defined to be directional. I mean, you could look at directional energy, but the way that physics is just defined, um, potential and kinetic energy are not directional. So kinetic energy is the energy an object possesses because of its motion. So anytime an object is moving, it has kinetic energy, and how much kinetic energy it has depends on how fast it's moving and its mass. So the faster an object is moving, the more kinetic energy it has. The more mass it has, the more kinetic energy it has. Really, really important, energy is transferable. So momentum is transferable as well, which is the next thing. So if something has high energy, such as us, we're moving fast, we can transfer that into the ball through force or work. By pushing into the ball, we can transfer our kinetic energy into the ball, making it fly faster. Does that make sense? If anything doesn't make sense, leave a comment, because this is not perfect. We want to make it clearer, and it might even be slightly wrong in points, and want to make it better. So, but well, this has been reviewed by uh, physicians, engineers, and stuff like that, so it should be pretty legit. Okay, momentum. I decided to show momentum as being orange and dark red because momentum is a function of, and we could use kinetic energy in the same way, could be colored the same way, because momentum is movement, but how much momentum has depends on the mass that it has. Velocity should be orange here. So the heavier I am, the more velocity I'm going to have when I'm moving. If I'm a fucking train, I'm going to have way more momentum than if I'm the 153-pound human I actually am, right? So greater the mass, the greater momentum, greater velocity, the greater momentum. Difference between momentum and kinetic energy, which is important, is it's directional, it's a vector. So we can say I have momentum upwards and I have momentum forwards, and like kinetic energy, momentum can be passed from one object to another. So the more momentum we have, if we push or we pull into an object, we can transfer that. So if we get good momentum going into our shot and push into the ball is going to go flying. Okay, a few more definitions. Work. Work is the transfer of energy and momentum from one object to another. Work affects movement. Work causes motion. So work describes force times distance traveled. So work is pretty similar to force, but it depends. It's like work done, the sum of the force done, right? So if we move a ball a long way, we have moved the ball with force times how far that ball is moved, right? Or rather, force times how much we have applied force and the distance that we have pushed into the ball, right? So work is a sum of force, kind of. Force times distance traveled. Right, all right, moving on. There's other physical terms and definitions, but these are the basic ones, and that's plenty to understand almost everything we need to know about physical laws of the universe, and specifically for shooting. So, quickly review, we have work, we have momentum, we have the energies, we have force, mass, acceleration, and all this is used to describe the interactions between objects resulting in motion. Why is there an and here? Red, dark red, orange. Okay. Moving on, we're just going to go over Newton's laws of physics, and we're going to go over Magnus Force and gravity. But Newton's laws of motion, physical laws that lay the foundation of mechanics, these are super important. Newton's first law, object at rest stays at rest unless acted upon by a force. An object in motion stays in motion unless acted upon by a force. So if the ball is just sitting on the ground, it's going to stay in the same spot. If we shoot a ball to the basket, the horizontal velocity is not really being acted on by much more than air friction, so it's going to more or less stay in the same horizontal velocity. Newton's first law is also called the law of inertia. Okay, Newton's second law is more important. This is force times mass acceleration. We've already dealt with that. Newton's third law is really important. For every action, there's an equal and opposite reaction. In every interaction between two objects, there are a pair of equal and opposite forces acting on the two interacting objects. The size of the force in the first object is equal to the size of the force in the second object, and is in the opposite direction. So for instance, if I push into the ground pushes into me, and it pushes in the opposite direction with the same amount of force. But since the ground has much greater mass than I have, and the force equals mass times acceleration, the ground is going to stay in the same spot, but we're going to move upwards. So that's a really important principle of everything, is ground reaction force. We apply force in the ground applies force into us. You listening right now, you're applying force in the ground or the chair or whatever, but you're not moving because of static friction. But once you apply enough force to overcome static friction, that's when you move upward into a jump. That's when you have upward motion, you contain kinetic energy, you have directional momentum, and you can push and transfer that into the ball, and that's how shooting works. So every action, there's an equal and opposite reaction. Look at gravitational pull briefly. First of all, it's just important to know that you need to shoot the ball really high to overcome gravitational acceleration, gravitational pull. So a lot of this book is going to be dealing with arc, how to shoot the ball up, not just forward. Gravity is a downward pull that causes a constant acceleration effect. This should be black. As an object is in flight, gravity accelerates the object downwards. The longer the object is in flight, the more gravitational acceleration has affected it. So basically, the longer we're in the air, or an object is in the air, the faster we're moving downward, the greater our downward velocity. Specifically, it's 9.8 meters per second squared. So that really adds up fast. Ignoring the effects of air resistance, the speed of an object falling freely near the Earth's surface will increase by about 9.8 meters per second every second. So that is really a huge effect. How gravity pull affects shooting. So we release the ball here. We have our upward directional velocity and our forward velocity. Gravity is causing downward acceleration, red pull, push force towards the Earth. And that is causing the direction of the velocity to be more and more downward. At the peak, we have no downward velocity, no upward velocity. The ball is not moving up or down, but this force is continuing to act at every point along this line, at which point, finally, at the end of the shot, the ball has downward velocity, or it has downward velocity immediately after this, but it has the greatest downward velocity immediately before hitting the ground, ignoring this interaction here because it has been in the air for the longest time. It's been affected by gravity for the longest time at its greatest downward velocity. So in order to hit shots, we might need to shoot really high in the air, and we're going to be going to that more in depth later. Last force to consider is Magnus Force. Magnus Force describes air resistance on a ball in flight depending on the ball's spin, shape, and position. Depending on how long the ball is in the air, depending on the shape of the ball, depending on how fast the ball is spinning, it can have a great effect. So Magnus effect operates in the following manner. This is semi-complicated, but say that this soccer ball is spinning in this direction, football in this direction, it has backspin. Magnus Force is going to lift it up, so it's going to give it greater lift. If it was spinning the opposite direction, it would be pulled down. It would have, we'll get into this greater detail. Top spin causes the ball to sink. So if we get the seams of the basketball in the right place and we get a good amount of backspin, it could keep the ball in a straight line, give it an extra boost in the air, which gives us extra arc and gives us extra accuracy. So seams grab a thick boundary layer. Yeah, this is really important in baseball, more important in baseball because you get way more rotations per second in a spinning ball than a basketball, but it's still relevant. So we're borrowing ideas from baseball here because it's been greater studied in baseball than basketball. But if you want to go into the kinetics of it, there's going to be a link here in the document, which you can get by dropping your email below, etc., etc. Magnus Force affects the ball flight in various ways. So if we have asymmetrical release spin, or we have asymmetrical seams position, like we have side spin or the ball is not lined up, we can cause the ball to curve side to side in flight, and that can be a few inches, which can affect percentage quite a bit. Lack of release spin can cause the ball to knuckle unpredictably, so ideally we get the ball in the right position with backspin, and it's great. Final look today, getting the physics of making a basket. So a hoop is a vertical target. We need to move the ball vertically upwards so that gravity can help it fall through the target. We also need to move the ball horizontally forwards to the target. We need to aim not too far left or right. We will need to account for left or right momentum. If we're moving left or right into the shot, we're going to need to cancel that or adjust our aim, which we'll get into. In order to move a ball vertically upwards, we must apply force into the ball from below against gravity pull, which we can do by applying force into the ground and transferring it upwards. There's other ways to add speed to a ball without necessarily putting more force into the ground. Applying force will accelerate the mass of the ball upward to the point of release and transfer kinetic energy in the moment of the ball. In order to move a ball horizontally forward, we must apply force in the ball from behind. Applying force will accelerate the mass of the ball. This is why shooters jump forward frequently. Applying force accelerates the ball, etc., etc. Up to the point of release. Once we release, that's all we've done, all that we can do, and we will get into deceleration as well, because follow through is important. That's a place where injury can happen. In order to hit the target, we need to release the ball at an angle not too far to the right. And then finally, we need to consider seams position. And that's basically that everything that goes into shooting. This is the physics of shooting. We're going to start getting into the mechanics, showing how professional shooters do it, put force in the ground, transfer it up the kinetic chain, so on. So, hope you enjoy this. Next video, it's maybe a couple days or it might be a week. Accuracy is a function of arc, range, and aim, and understanding. So we're going to start looking at arc, range, and aim, and that might not be physics and mechanics of arc and range. This is going to be a pretty mathy section, and after that we're going to start going into real breakdowns of Steph Curry, Ray Allen, Kyle Korver, and stuff like that. So if you want to stay updated and you want to get the link, drop your email below. Let me know what you think in the comments if anything is confusing or sounds wrong to you. We would love to have a discussion. And again, if you're a subscriber, check your email because you should have a link to it in here. So much love, shout out to the shooters. Peace. See you in the next video. Happy shooting all.